Let's take a look at an example problem from Module 9 for ME12 Dynamics. So in this problem here, they show us a diagram where we have these two slider blocks A and B, and we have some rod in between them here. And they tell us that the two slider blocks are connected by the rod that has a length of 2 meters. They also tell us that V sub A, slider block A, has a velocity of 8 meters per second. So we can see that down here. It's moving to the right at 8 meters per second. And that slider block A also has an acceleration, A sub A, of 0. Now they want us to find our angular velocity, our omega term here, and our angular acceleration, our alpha term, of the rod when our theta angle here is equal to 60 degrees. So for our plan of attack to come up with a solution here, first we want to choose a fixed reference point and define the position of slider A in terms of our parameter theta. So we're going to define our slider A in terms of this parameter theta here. Notice from the position vector A, positive angular position theta is going to be measured clockwise. So we're moving this around clockwise like this here for our positive angular position. So now that we've had a chance to go through, read our problem statement, take a look at the initial diagram, and understand what they're asking for, we can now create our setup page. So in our setup page here, we have this example problem here. I redraw out my diagram in a little bit simplified form here. Slider block B up here, slider block A down here. I know this velocity is 8 meters per second. I have this theta term here, and I know the length of the rod is 2 meters. So I redraw that out. I write down my givens over here. So I'm given the fact that V sub A is equal to 8 meters per second, and A sub A is equal to 0 degrees initially here. So we have to find our omega term. So now as we begin our solution, we can reference back to our setup page and our problem statement for any information that we needed to plug in. So the first thing I want to do with my solution is I draw a simplified version over here, just a simple triangle of our setup. So we can see, okay, I have this length of this rod here is 2 meters. I have my theta angle down here. This is at 90 degrees. And I want to figure out this distance from the end over here to the end of the rod here, from B to A, for this value of SA. So I can do a little bit of trigger. Recall that the cosine of theta is adjacent over hypotenuse. So I have my adjacent over my hypotenuse there. So I can plug in my adjacent is my SA, my hypotenuse is my 2 meters. So therefore I can back out S sub A is equal to 2 times the cosine of theta when I rearrange and solve for SA. So from that, what I need to do next is I want to find VA. So we'll take the derivative of SA with respect to time. So as we recall, velocity is the first time derivative of position. So we take the first time derivative d over dt of our position SA in order to get our VA. So we say VA is equal to d over dt, and we can plug in now our relationship from SA from up above here, plug that in. That's 2 times the cosine of our theta term there. Now from this, to take that derivative, what we can do is we can use our chain rule. When we do that, we find that V sub A is equal to negative 2 omega times the cosine of theta. So now we have an expression for V sub A relative to our theta term. Next thing we want to do is use our known values here. So we'll use our fact that we have theta given to us at 60 degrees, and our initial velocity of A, V sub A, is equal at 8 meters per second here. So I can plug into this equation that we just came up with for V sub A. V sub A is equal to negative 2 omega times the sine of theta here, where we have a V of A and we have a theta. Our only unknown is our omega term, so we can plug in. V sub A is 8 is equal to negative 2 omega times the sine of our theta of 60 degrees. So our only unknown here is our omega term. We can rearrange and solve for our omega. We can move a few things around, rearrange a little bit, and we end up being, okay, we'll divide the side by 2 over here. So we're left with negative 4 is equal to omega times the sine of 60. Get omega by itself. So what we end up looking at is we divide our sine of 60 across the other side. We have omega is equal to negative 4 over the sine of 60 degrees. Or if we solve that for omega, plug it in, omega is equal to negative 4.62 radians per second. Now, this negative sign indicates that the rod rotates counterclockwise, CCW, as point A goes to the right. So again, I always like to, as I'm doing these types of problems, especially the simple systems like this, as things are moving, pretend I'm moving it to the right and see how every other component acts within that system. That's going to help us. So that's exactly what we do here in order to find out that this negative sign does indicate this counterclockwise rotation, and that does check out. Now next we want to find our alpha term, but to find our alpha term, we'll first need to find our acceleration term. So to find alpha, we take the derivative to start off with of that v sub a. So recall acceleration is the first time derivative of our velocity position, so we take d over dt, first derivative with respect to time of our velocity position. We have now an expression for our velocity v sub a, so we can plug that in down here. So the acceleration at a is equal to d over dt of negative 2 omega minus the sine of theta here. Now for this here, what we can do is we can do our chain rule and our product rule within this here. So we end up with for our derivative here of our VA, negative 2 omega prime, derivative of the first, times the second is our sine of theta, plus the first, negative 2 omega, times the derivative of our second, which is the derivative of sine of theta here. So then we can do this here using our chain rule there. What we end up with is our a sub a is equal to negative 2 alpha times the sine of theta minus 2 omega squared times the cosine of theta there. So now you can see this is where our alpha term came in. Now we're given in the problem statement that our a sub a is equal to 0, only at a constant velocity at a, so this becomes 0 there, is equal to negative 2 alpha times the sine of theta minus 2 omega squared times the cosine of theta. So from that equation there, we can rewrite this up here, and what we want to do is solve for our alpha term here. So I can move things around and rearrange in order to solve for alpha. Let's move some of this over to the other side, so we can take this here, put it over on the other side, get rid of the negative there, so we'll end up with 2 alpha times the sine of theta is equal to negative 2 omega squared times the cosine of theta here. Let's divide both sides by 2. When we divide both sides by 2 here, we can end up with this expression, alpha times the sine of theta is equal to negative omega squared times the cosine of theta. So then we'll divide both sides by our sine of theta here. So we're left with just an alpha on this side here. So alpha is equal to negative omega squared times now the cosine over the sine of our theta term right there. So we can call this as a trig identity here. Cosine over sine is equal to 1 over our tangent here, because sine over cosine is tangent, so cosine over sine will be 1 over the tangent here. So alpha is equal to negative omega squared times 1 over our tangent here. We can put this omega squared term on top here next to the 1. So alpha is equal to omega squared over the tangent of theta. Well, we have known values, so we can start plugging in our known values. We have our omega term that we solve for as a negative 4.62, and we have our theta term given to us as 60 degrees. So we can plug those both into the equation, and then we can solve for our alpha term. So our alpha term ends up being negative 12.32 radians per second squared for our alpha.